Okay, and now for something completely different. And actually, I won't be talking about what I said I was going to do.
Never mind.
But it's going to be more fun this way. And I'm kind of picking up from actually where Dorian left off. And I'm going to just start you off looking at a very simple climate model, one that would be accessible to Dorian's astronomer. So what we're going to do is find a working laser pointer. Let's try this one. Okay, that's good. So we're going to get energy in equals energy out. And what we're going to say is that the solar not constant times 1 minus the albedo is going to equal the outgoing long-wave radiation. And I've modelled the outgoing long-wave radiation here as just the surface Planck function. I've let my albedo as a constant. So I can match up these two graphs. This is something that you would think even students from BC high schools would be capable of. And you get a temperature. So that's basically what we're going to do for this talk. So this is roughly what we're going to do. I am going to restrict it to Earth-like planets. That is, planets I understand well, which are rapidly rotating, have water as their condensable component, and at a kind of temperatures that we know something about, that we might have experienced. And I'm going to turn the temperature up and down and see what happens. And then I'm going to do really difficult things like change the amount of CO2 in the last slide. So this is revision from Dorian's talk. We have two big instabilities in terms of the amount of ice we have. Ice is cold and also reflects sunlight away. So we have a large ice cap instability, which is we let the ice develop down to anywhere below, substantially below Canada. Let's get it down right down into the US. And then at some point it'll get too far down and we'll go to globally ice covered. There's also a small ice cap instability, which is we let the ice recede too far to the poles and pip, it's all gone away and we're in a totally ice-free state. So we could plot up the ice line latitude here, and also our co-albedo. And we can see 3 different climate states with 3 different characteristic albedos, and rapid transitions between them in global mean temperature space. And then one could imagine drawing on the surface Planck function for emission, drawing it on like this, and it would cross here an arbitrary number of times, and that would be the number of different climate states that we would have. And this is how often we think about Earth in terms of glaciation, but I'd like you to think a little bit harder based on what's actually happened on Earth. And our top line here, it really represents what might have happened in the Cenozoic. That's the last 65 million years since we killed off the dinosaurs. And there's a key thing of the ice sheet altitude feedback, which is that you build up an ice sheet and the top of it gets quite high in the atmosphere. The atmosphere gets colder as we go up. So once you've built up an ice sheet, that ice sheet is inherently more stable than if it was not there because it's cold at the top. So it's good for keeping your ice or avoiding ice melt. Ice melt is what you need to avoid to keep an ice sheet. So we've cycled for the last couple of million years between glacial conditions and interglacial conditions. We are in an interglacial now. And that transition is switching on and off the Fennoscandinavian and the Laurentide ice sheets. They don't gently recede and gently advance. They turn on and off catastrophically. We go back to the Oligocene. So 30 million years ago, that's when we glaciated Antarctica. We go back to the Eocene, or also more recently in the mid-Miocene, we had globally ice-free. So we have these transitions which are non-linear between different states. And we could also go to Dorian's water belt solution, or snake which wraps round the world, which he may or may not believe in at this time, who knows. And you could say that we can invent a pan-glacial state with stable liquid water at the equator. For the purpose of the talk, I do not care whether Dorian believes in that today. So what happens if we put them on the same diagram? Well, it gets a lot lumpier. We have transitions in the ice line latitude which I've just sketched out schematically here with a bunch of little humps on the way. So you could imagine that for any given climate, you could have, in terms of the ice line, probably 5 or 6 different stable climates, depending on just how you matched up your outgoing long-wave radiation through here. And that is what we have seen in the last 500 million years of Earth when we've had a good geologic record. We've seen a certain set of ice sheets turn on and off. Which set of ice sheets you can turn off depends on the random drift of the continents around the surface of the Earth. So this shape here will change with time, whereas these bigger features may not. But now I'd like to do something I think is a little more interesting. I'd like to talk about the amount of water vapour. And water vapour can vary in terms of how much of it we have in the atmosphere. And it's really cool how it does that. So we're here in Houston, and there are 55, or as of 7 p.m. last night, there were 55 kilograms of water per metre squared in the atmosphere. And this is a colour scheme of that, and anywhere in this cyan colour here is 50 to 60 kilograms per metre squared of water. If we go down to the Antarctic here in the winter, we're less than 2. The mid-latitudes here are between 10 and 20. So if you look at this small distance here of a couple of 100 kilometres, we're varying by more than an order of magnitude in how much of an atmospheric constituent we have. That is incredibly weird. That should keep you awake at night if you think about planetary atmospheres. It's really hard to get more than 50 or 60. That's all the cyan. The little purpley spots in here that you can barely see are where it gets above 60. Hurricane Jebi at the moment, that has got, I forgot to label it, it's down here, 80 kilograms per metre squared. That's really good. It turns out that what needs to happen is it's very easy to make the boundary layer moist. But to get the 3 tropopause up towards 100% relative humidity, or even, much above, in a mean sense, 40% relative humidity, needs real work. And that is what Maura Dewey's talk, which is the last talk today, is all going to be about. And that's a phenomenon called the super greenhouse effect. It's really driven by deep convection, really getting moisture aloft. But that's really hard work. So what's this going to actually look like if we look at a temperature and then the amount of water vapour in the column? Well, the boundary layer in blue here is going to be pretty easy to get saturated, whereas the 3 tropopause, we've got to get warm enough that deep convection happens, and then there's going to be a non-linear transition associated with the super greenhouse to get up to a saturated 3 tropopause. So what is that going to happen? What's that going to do in terms of the outgoing long-wave radiation? So on the right-hand side, we've got the runaway greenhouse, which various people have talked about, and I'm not going to bore you to death with another talk on the runaway greenhouse from me, which many of you will have heard too many of. But now we're here. We've got this super greenhouse that Maura's going to talk about, this bistability which may apply to the tropical atmospheres today that would get us to a moist greenhouse state. And then we've got this transition to a runaway greenhouse. So if we imagine that the amount of solar constant, naughty Colin, solar not constant, if we imagine that the albedo didn't change, we could draw a line straight across here, and we could have 3 different fundamental climate states just from the water vapour for present solar constant. We could have temperate climate, we could have a moist greenhouse that's like the tropics everywhere, or we could have the runaway greenhouse, which, well, we wouldn't experience that ourselves. But if we go beyond that single column, what actually happens in the atmosphere? And these are our regions of the atmosphere shaded in blue here, where we actually have a serious amount of water vapour in the atmosphere. It's totally dry around a snowball Earth. We'll get a little bit of moisture up here above Dorian's moist regions. That sounded so bad, I'm sorry. It's the last day. But we're going to really build up the size of the moist tropics here until, and there's a wonderful paper by Matsaki Ishiwatari on this, of going to a fully moist atmosphere as a transition here. So in the same way that we move the ice line down, we also move what I'm going to call the moist line out from the tropics. So what might that look like? We've lost a few labels here, but we're going to have transitions in the atmospheric wetness, which are going to be non-linear. We're in this climate state here where we've got dank mid and high latitudes of the moist tropics, but we could move to a thoroughly moist tropics, or we could get rid of them. And these will happen in steps. And that is the thing, is Earth's climate is replete with non-linearities. So if we add all of them together, if we add in our solar constant times co-albedo, and then match it up to the red line that we were just talking about, that's where we can get the different stable climate states. So this is how I'd like, if there's something I'd like to take away from this talk, it's to think about habitable planet climate not as a monolithic thing, but as there's many different states which are actually very distinct from each other. We turn up or down the solar constant, we can sample different ones of these states. Now, here are some of these states. What have we got? You can say that many are habitable, some are icy, some are cloudy. I haven't really talked about cloud here, that'll have to be a different talk. Suffice to say, this will be cloudy pretty much everywhere, as will this, and there aren't many clouds down here. And on some of them, we'll be able to observe water vapour, all of which are probably habitable. This is the last slide. It would get more complicated if we changed CO2, because we would change the shape of these curves. So by turning up or down CO2, something that's quite internal to the planet, we can exist or non-exist some of these climate states. We could also do it by changing dinitrogen, which will change the reflectivity. A couple of last things while I'm talking about this. One is this has kind of been a bit of a review / hypothesis talk. I'm thinking of writing up something like this, either into a review paper or into a model which would hopefully show all of this. So I'd love feedback from people, both the people who've been doing this rev and the people who haven't, as what would you find most useful? Would you like to read a review paper like that? And if you're graduating soon and you want to come work with me, come talk to me. Thank you.
Is there geological evidence for the Laurentide ice sheet and the other ice sheets in Eurasia kind of growing and retreating, on very, very short timescales? So I misspoke slightly. It takes quite a while for the ice sheets to grow, because you've got to build up that ice, but deglaciation happens very rapidly. And the best evidence for that is in the oxygen 18 from benthic forams. You can look at the amount of ocean volume, and you see the ocean volume goes down slowly and then up quickly. And that's a beautiful isotope record.
Are there any other questions?
Just a quick comment. I think ocean heat transport can influence the state that you proposed. The ocean heat transport can influence where the ice age state.
Yeah, I think it will. Now the question I'll throw back to you is: do you think if we had ocean heat transport rather than just atmospheric radiative transfer and thermodynamics, would we have more or less climate states?
I think less.
Less? Okay, well that's a challenge. I'll take that on. I'm going to keep all my states with ocean heat transport.
I have some simulations.
Okay. Thank you.
Include ocean heat.